I'm going to jump right into things because I have a huge amount of content to go through today, and I'm really excited about it. Today we are talking about the processing side of processing aerial LiDAR data for land surveyors in particular. And as a reminder, this is part 3 of a 3-part series. We already went through part 1 about the LiDAR ecosystem, the technology, how it compares to photogrammetry, some high-level data processing, as well as the business side of things, actually building a team, analyzing it, hiring people, running it, making sure that money makes sense. And today, we are talking about part 3, actually processing the data. So if you want to reference those other 2 parts, they're there on YouTube. I might be referring to them at some points as well, but all of this is going to be available online shortly anyway. But to dive right into it, what we're going to cover today, as I mentioned, is all about processing aerial LiDAR data. And the way that I view it, the way that we've kind of analyzed it, is there are 3 really major steps to processing aerial LiDAR data. You fly a drone, and then what? What happens after the drone lands, after you fly it? Well, step 1, you actually need to take that data and turn it into a good point cloud. And I say good because there very much is a difference between a bad point cloud and a good point cloud. So processing it, actually turning the raw data into an LAS file, making sure that it's accurate, making sure that it's geo-referenced, all of that is really important. And then at the end of this, we're going to go through technology for step 1. And this is something that you'll see. A big part of working and processing data is going to be the software that you use. What software, what computers, what hardware. And so at the end of each of these 3 steps, I'm going to go into the software that we actually use, the software that other people use, what our favorites are, a little bit of the differences in there. And that's going to be the same for all 3 steps. So then we get into step 2. Once you actually have a good point cloud, how do you process it? What do you do? How do you create ground classification? How do you turn your ground classified points into a surface, a nice rasterized DEM or something like that? Feature classification, extracting buildings, power lines, power poles, all of that. And then, of course, technology for that step as well, all of the software that we're going to use there. And then step 3 is how do you actually turn all of that into a map? There are a lot of people that either stop at step 1 and say, here's an accurate point cloud, that's good enough. Or they stop at step 2, here's a classified point cloud and think that's enough. But we think it's really important to actually go one step further and actually turn all of that into a map. And now I'll go through all of the rest of the intro slides really quickly because this is part 3. If you're with me today, there's a good chance you've seen some of our other webinars. But just as the very brief reminder, we are Aerotas. We have been doing data processing for over 10 years now, including processing huge amounts of LiDAR data. And of course, that gives us the data and perspective that has been battle tested by tens of thousands of LiDAR projects. That's where this information comes from. And that's why we're sharing it with you. And of course, again, our company perspective, our fundamentals that go through all of our other slides, all of our other projects as well. We think that we should help you build a drone program that saves time, costs less, and improves deliverables. It's not about a science project. It's not about proving that you can do it once. It's about how you turn this into a business. And if you do all of this right, it absolutely fundamentally, completely is possible to have a LiDAR program that saves you time, costs less than the alternatives, and gets you better quality deliverables. It is possible to do that. And the way to do that, of course, is through finding balance. Again, you've heard it from me a bunch before. You're going to keep hearing it again. And that's how important this is finding balance. Accuracy at the cost of literally everything else leads to a very bad business, and you don't actually use it much. Likewise, if you focus only on getting the cheapest quality equipment, you're going to get a bad drone program as well. It's all about balancing all of these things. And as we go through and talk about balance, one of the other fundamental things that I want to talk about is that there is no one way to process LiDAR data. A lot of you might be coming here saying, I want to learn exactly the workflow. I have LiDAR data. How can I process it? And quite frankly, there is no single unified workflow, much in the same way that for land surveying, there is no single unified workflow that actually goes all the way from A to B. You can use GPS, you can use a total station, you can use different GPS setups, whether you get an open solution, blah, blah, blah. There's so many different ways to do it. And ultimately, each company will have different equipment, whether it's drone LiDAR equipment or their GPS equipment, what setup they use. They'll have different software. Maybe you're in the Leica ecosystem, the Trimble ecosystem, or something else like that. different project requirements, how much vegetation there is, how difficult it is to actually reach different places, set up ground control points, things like that. Different priorities. Maybe you prioritize speed for a project that needs to get done really, really quickly. Maybe you prioritize reliability or making sure that you don't have to go to a site revisit. As well as capabilities. Some people are really, really good at things like advanced GNSS processing. And quite frankly, that means that every workflow is unique, and ultimately that is okay. So I'm going to try and keep this flexible to the point where I don't just tell you exactly how we do it, though I will be telling you that, but also all of the different ways that you can do it. Because again, like the workflow will change depending on your hardware setup. If you have a DJI L1 or L2 system, it's going to look a lot different from a software perspective, particularly at the beginning, that kind of initial step, than if you have a GeoQ TrueView system and you're working through LP360. Same thing if you are using a DJI base station or a Trimble base station or an N-Trip permanent base station, network base station, the way that you process your GPS data and align your point clouds is all going to be a little bit different. And again, that's okay. I'll point out the different workflows, but not everyone will have the exact same workflow. And your brief reminder, of course, that's what we do. We process data, whether it's LiDAR, photogrammetry, topo mapping, all of that. That's what Aerotas does. If you haven't heard of that by now, then just making sure that you do. But this isn't a sales pitch. This is actually meant to be a technical webinar, so we're going to get into it. And another one of my just kind of high-level reminders that I always give, the end goal is a map, not a flight. And likewise, the end goal of LiDAR processing is not a LiDAR point cloud. At least that's how I view it. Some people think the end goal of LiDAR processing should be a point cloud. I don't think that is the case. My perspective, especially working like almost exclusively with land surveyors and civil engineers, the end goal is a map, not a flight. So we're going to go one step further because we want to make sure that these things are actually useful. All right, so let's now get into the nuts and bolts of it and start with, again, that kind of high level. So high level workflow, what happens is you fly the drone, and what you get with the drone, you have your raw LiDAR and IMU data. That's the LiDAR sensor and the inertial measurement unit that collects raw data on the drone. It's not a point cloud, it's raw sensor data. You also have your ground control data as well as all of your GPS, GNSS, RTK, PPK data, all of that sort of stuff. It's very raw data at this point. It's not particularly useful. You then go through that step one, which I call initial processing, and that gets you to an LAS point cloud. Your point cloud is going to be ideally, once you're done with initial processing, it's going to be accurate and it's going to be geo-referenced and it's going to be in the right coordinate system and as tight of a point cloud as you can get, but it's still going to be a fairly raw, unclassified point cloud. That's when you go through your point cloud processing. That's going to be classifying ground, buildings, objects, doing rasterization, things like that as much as you need, which gets you your classified points, ideally a rasterized DTM, as well as your kind of basic features that you've extracted, whether it's, edge of road or edge of pavement or curb lines or things like that, typically in kind of a lightweight DXF file format. Then you go through what we still call the line work drafting phase, which is extracting all the rest of those features that you may or may not need. Power pole tops and bottoms, transformers, brake lines, all of the other things that might go into a survey, as well as creating an ortho photo out of it to create your final map. This is the really high level workflow that we're going to be going through in detail. So step one is create that initial processing, creating a good point cloud. Now, initial processing, like I kind of mentioned at the beginning, starts with your raw drone data. This is this picture is an actually older drone that had some very manual data processing as well with a Regal LiDAR sensor on it. But as a reminder, the laser itself, the actual laser unit, only records the distance between the sensor and whatever it's measuring, and technically also the scan angle as well. But that needs to be combined with data from the GPS system, the IMU, the gimbal data for lever arm offsets, the imagery, which is actually where the colorization comes from. As a reminder, I'll cover this in a second. Raw LiDAR data, the laser scanner itself is a wavelength of light that is invisible to the human eye, and it is uncolorized. So color to a point cloud actually comes from the camera that is mounted with the LiDAR system as well. Now, this step is usually very heavily controlled by the LiDAR manufacturer. And so the software that you typically use in step one is going to be dependent on the system you have. And I'll cover it a little bit later, but for example, if you are using a Trimble or an Applanix system with an Applanix IMU, you need to go through a software called PostPack. If you are using a Wingtra one, you need to go through Wingtra Hub. If you are using a DJI L1 or L2, it goes through DJI Terra. So this is typically heavily controlled by the manufacturer, but tweaking it has a lot of other softwares in it later on. This is a slide that I think is most people probably don't need to know unless they really want to get into the nuts and bolts of how LiDAR systems work. But I actually spent a lot of time building this, so it's kind of cool to me. It shows the actual information workflow from the different sensors. So the way that a point cloud gets created in any of these softwares, the workflow is the same regardless of which software you use, whether it's DJI Terra or Applanix or any of these. You start with your GPS information, actually. Before you even touch the LiDAR system, most softwares start with GNSS data and IMU data, and the GNSS, that's your lever arm offset. All of the GPS data comes in first, is combined with the IMU to create a trajectory file. This is often called an SBET file or a smooth best estimate of trajectory. And what this is actually your trajectory information of where the software believes the exact position of the LiDAR sensor was as it is flying through time. So it's trajectory with time as well. And again, haven't even added in LiDAR data. Then you add in the raw LiDAR data, which is going to be the actual range, the distance from the laser scanner, the scan angle there, as well as the bore sight measurements. Bore sight is the alignment between the laser scanner and the IMU itself. And that creates your initial point cloud. I say initial point cloud because, well, you probably need to, depending on your system, either adjust your trajectory data, or maybe it's not georeferenced properly. It depends on where everything is. It's also going to be uncolorized. The next step is, once you have that initial point cloud, that is next when the RGB image data, the actual pictures are included to create a colorized point cloud. Again, the color gets added kind of partway through it. And then people typically add in their GPS base station data. Maybe they get an Opus solution on their base station. They have to correct it after the fact. Or you add in your ground control points to do that final georeferencing. And this ultimately is kind of the workflow to get you to that final georeferenced point cloud. And I will remind you, this is still what many people would call a raw point cloud. No classification done. It is georeferenced, it is colorized at this point, but it's still fairly raw. And now this is the system that all of these initial softwares go through. Now, the DJI software, DJI Terra is the most common one because the DJI L1 and L2 are unquestionably still the market leading hardware, right? You can argue and quibble about all the technology. You can look at my previous presentations. I'm not here to talk about hardware. But it is an undisputed fact that they have the largest market share and they are the most popular one. And so DJI has all of this data that you see. This is what an actual DJI project data would look like, which includes all of the information I shared before. And most people just dump it into DJI Terra and you get out a point cloud. And actually, it's usually pretty darn good just letting it be automated. This part has gotten way more automated lately, both with DJI and other softwares, but it's really quite good, and it is typically good enough for most use cases. Where this breaks down and where you can't let it be fully automated is in a couple of situations. Number one, if you're using any non-DJI hardware, there's typically going to be a lot more fiddling with your trajectories and with your SBET files to get everything to line up perfectly, which is time consuming, but definitely doable, especially if you want like ultra super duper supreme accuracy and reliability. Or the other alternative when you need to start fiddling inside of this under the hood is when something suboptimal happens with your GPS data. If your GPS data wasn't good, if you can't get a good, post-processing match, if your base station failed, if you lost RTK link, there are a lot of GPS and GNSS post-processing issues that can lead to a in the best of circumstances, a really janky point cloud, and it needs to be fiddled with in order to get it there. So I'll cover in a little bit all of the softwares you can use for this step one to cover everything, but that's what it looks like. Again, this is where the colorization happens. As a reminder, point cloud colorization happens after the point cloud is created, and it's worth noting that there is always going to be some error in the point cloud colorization. It is good, very good, but not as good as the point cloud itself. So what you see here on the left is going to be one that's colored by intensity. This is kind of what the laser scanner itself actually sees. And on the right is, of course, the color. But one of the reasons why there actually is some lack of accuracy in the in that color is because the camera only takes a photo about every 2 to 3 seconds, depending on exactly what drone it is, or assuming it even has a camera, which many LiDAR drones, many non-DJI LiDAR drones do not have a camera, so they're only going to be effectively black and white, only intensity data. But the colorization, you only get that photo every 3 seconds, but it's scanning LiDAR data the entire time. LiDAR data is scanned continuously. So all of that is to say that there might be a couple tenths of a foot worth of error in the colorization. It's really good for reference, but it's typically not great for 2D mapping. Again, useful, but imperfect when working with colorization. Just important to be aware. So even then, once you get that final point, that raw point cloud, you do need to do a step that I call point cloud refinement, or you don't need to. This is a step that depending on your project needs, how many flights there were, whether or not you move base station, but there are still a handful of remaining sources of error in your point cloud, what could be sources of error that need to be refined. For example, trajectory inaccuracy. If your GPS or your IMU is not perfect, which that happens, that's a fairly normal part working in the real world with real world amounts of noise, then you need to deal with manual trajectory refinement. I really, 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 really hate doing manual trajectory refinement, fiddling with the trajectory data. It is extremely time consuming, and most of the time, if your trajectory data is bad, from a business perspective, it makes sense to fly the site again and make sure you get good trajectory data. That's not always the case, but quite frankly, it's something that can be done. The most common software for that is called TerraMatch. I hate dealing with bad trajectory. Same thing with bore sight misalignment. Bore sight is when your IMU and your laser scanner are not perfectly aligned, and that can create a little bit of inaccuracy. Again, we're talking on the order of tenths of a foot, usually at worst. But again, you need to calibrate it from multiple strips where a flight flies back and forth and actually has overlap. I should point out, for what it's worth, all of this is part of the reason why in previous steps, we recommend slightly higher overlap than a lot of people. When you have slightly higher LiDAR overlap, it makes these problems so much easier to identify and solve in an automated manner without having to deal with any sort of manual fiddling. Another major source of error, especially for larger projects, multi-flight alignment. Typically, with any project flown where you either have, it's big enough that it requires multiple drone batteries, or it's flown over multiple days, or for example, you're flying a 10, 20, 30 mile corridor or something like that, and you have multiple flights, each one of those flights may not align perfectly with the other flight. There are a number of different ways to get these to align, either from downstream GNSS processing, getting Opus solutions on different base stations, as well as using ground control points. We are big proponents of ground control points in general. And then also project-specific georeferencing. I bring this up because surveyors are very, very, very used to georeferencing. It's not a surprise to say that this product needs to be done in this NAT 83 zone with this scale factor. That's common for surveyors. But among LiDAR specialists and drone specialists, they see the world almost exclusively in WGS 84 lat long with ellipsoidal height. And that's not how survey works. So you actually have to georeference it. You might need to perform some transformations to get it to match up with your local coordinate system. This is a huge source of tension in the industry because drone people don't understand georeferencing. Surveyors absolutely need good georeferencing, and we see those errors all the time. There are lots of ways to handle it, but typically this is one of those things that most surveyors understand the importance of project-specific georeferencing, and a lot of drone-specific people don't. When you are lining up either multiple swaths to do manual trajectory alignment or multiple flights for flight-by-flight alignment, it's important to make sure they line up with them, but it is also important to be aware of all types of shifts that you can have: vertical, rotation, scale. The three main ways to do this: advanced GNSS processing. I say advanced, getting an Opus solution isn't all that crazy advanced, or doing a PPK on a known base station or something like that. But that definitely works. Alignment with ground control is definitely a very, very highly recommended one. Having good ground control data helps on so many different levels. Or you could just do pure point cloud alignment, where you physically just visually make the point clouds match up. We generally consider this to be the worst option, because it can kind of sweep other errors under the rug and make it look more accurate than it is. But it can be done in many cases where you just kind of do a almost dead reckoning. When you are georeferencing your point cloud and then getting to that last step with project-specific georeferencing, we really like ground control points for survey, at least. Again, many LiDAR manufacturers, the systems themselves rely on GNSS alone. That's fine, but we really like localizing with GCPs, although it's not without its challenges. GCPs, ground control points, can be difficult to see. The image you're seeing on the right is an actual project, actual ground control point. We can identify it very easily in the ortho imagery with the photogrammetry. It is much, much more challenging with LiDAR, and goes back to what I was saying a little bit earlier. It's part of why photogrammetry is just so much better for identifying 2D features, whereas LiDAR is often better for doing topo and vegetated areas, things like that. But that's what an actual ground control point looks like on an actual project too. You can use intensity to find ground control points as well, to georeference a project when you don't have colorization. That works. Just make sure you have high contrast ground control points. Black and white, or the ones that that we sell that are pink and black, actually really pop too, even in invisible color color ranges. And another slide that I mentioned in all of my flight ops things, people ask, well, if the LiDAR GPS is so good, do you need ground control at all? And my answer is the same as with photogrammetry here. Yes, good GNSS is technologically capable of producing survey-grade accuracy with no ground control. However, and this is a big, big however that I think most surveyors will understand, in the real world, no ground control is simply not good enough. Ground control is required to properly calibrate the system, make sure that your bore site errors are actually there, that you can localize it to your project as well. And the most important thing for ground control is actually both measuring and monitoring accuracy and detecting errors, because human errors remain so common. The more complex the workflow, the more likely a human error is going to slip in there. We have seen literally every possible form of human error you can imagine, and then some. Having the ability to correct errors, to catch errors early and correct from them, is just responsible from a simple mapping perspective. If you are only relying on GPS data, man, you are playing with fire. Ground control is really, really, really important for anything that would be qualified as survey, to actually make sure that it's there. Which gets us to accuracy verification. I'm going to breeze over this incredibly quickly because, quite frankly, I have given numerous other talks about accuracy, which we will send you, by the way, for anyone here. If you're watching on a video afterwards, there will be more resources in the description below. If you're with me live, we will be emailing out a lot more resources, including webinars that I have given explicitly on accuracy. But to sum it up really, really quickly, the way to measure and certify accuracy is you set independent check shots or checkpoints, same difference. You measure the error and you report the error. If you're doing that, you're 99% of the way there. Set check shots, measure the error, report the error. If you really want to know more, like I said before, you can watch my video. Here's just what the YouTube video is, one of the best ones that we have online. And all of it refers to the ASPRS positional accuracy standards for digital geospatial data. This is definitely the gold standard for understanding exactly how to measure it. They have huge sections on LiDAR accuracy measurement and verification as well. So that's really important. All right, so that's step one, but I know everyone wants to know about the technology. And this is actually really, this is a tricky part for me. When I first started putting together this presentation, I wanted to do a lot more like, let's go through some of the software. Let's point it out how to use it. I'll teach you some of this, show you the software that I use. And what I was realizing is that, first of all, my goal is not to give a specific single software tutorial here, because quite frankly, here is a incomplete list of these softwares that are used only in step one. It's crazy how complicated this software ecosystem is, which is one of the problems with it. And actually one of my biggest criticisms and where a lot of people get stepped up or get caught up. So a lot of the big ones, for example, a Planix PostPack or DJI Terra or things like that. Novatel has some software as well that actually does some of the initial trajectory creation. Like I said, these are going to be the initial ones that are going to be heavily driven by the manufacturer. I'll highlight a few of the ones that I actually like in here as well. RTK Library is a open source software that we have used a lot successfully for GPS processing. It's not very easy to use, but it's open source, which means it doesn't cost a dime. TerraMatch is definitely the gold standard for fiddling with trajectory files and bore side alignment with any system you can actually use. You can even get DJI data into TerraMatch to do better trajectory alignment there as well. And then when you get into TerraScan and Global Mapper Pro, I am most familiar with Global Mapper. That's kind of a GIS and LiDAR tool. It's a Swiss Army knife, jack of all trades. Do I recommend it? Absolutely, unquestionably, no. It does some things better and some things worse. The hardest part about a lot of these softwares is that there is no one best one. Even within Aerotas, we have some of our LiDAR techs that like different softwares, and they both produce really, really good data, but it's just some personal preferences, what you're familiar with. And another thing that makes it hard is that the learning curve on any of these software is quite long. It takes a long time to learn them, to understand what you're doing, and to go from there. All right, so that's some of the software used in step one. Let's actually jump into step two, or maybe I'll pause for just a second and see if it looks like no one has asked any questions yet, which is totally fine. I'm that good of a presenter. But if you want, there is you can always hit the multiple dots button. There's a Q&A section if you want to ask questions while we're going through here live, and I will try and get to them as best as I can. But since we are already about halfway through the time, let's jump into the next major step in this, which is going to be point cloud processing. So we've been through step one. Now the assumption is when we get into step two is that we already have our accurate geo-referenced colorized point cloud. That is the starting point to going into step two. And the first thing that I always do, or that any of us do here at Aerotas at least, is ground classification. You don't have to do ground classification first, but that's typically what we do for a number of reasons. For starters, because the most common thing that people will fly LiDAR for, or the reason they're using LiDAR to begin with, is to get a topo map. Generally, if you don't need topo data, you wouldn't be using LiDAR to begin with. You'd do photogrammetry only or something like that if you didn't need topo. So you almost always, in basically everything we do, we start with ground classification, which is taking that raw point cloud and classifying it ground and non-ground. And as usual, I always like to start with take a step back and ask some of the trickier questions that few people ask. For example, what is ground? It seems like a simple question, but it really is hard, and in many ways is project dependent. For example, if there is a pile of debris, a whole bunch of concrete and concrete dust, is that the actual ground surface, or is that an object that you classify and you put the ground underneath it? Same thing with sock piles. Same thing with things like rock outcroppings. There are plausible cases to be made that rocks are part of the ground or that they are an above ground feature. And the problem is this happens everywhere, right? Like there's some things that are really hard even for humans to judge. One of the more interesting ones is we see a lot of, there are cars everywhere, obviously, wherever, pretty much anywhere in the world. But cars, especially when they have, they're cars that may have been there for a while and they have a tarp thrown over them, look an awful lot like just a pile of debris, maybe a pile of dirt. Sometimes there's so much other stuff and plants around it that you cannot tell if it is a car or a pile of debris, even with advanced analysis. So what is ground? This is one of the trickiest questions for a LiDAR data analyst to actually define. And now, thankfully, there are standards for these things. The most important thing is actually having standards, defining them clearly, and making sure that you know whether you're going to mark rocks. But even once you know what ground is, you have to teach your automatic ground classifications. Automatic ground classifications are very, very good at following basic routine tasks. If it sticks this far above the ground and it's this steep, then it's not ground. But automatic ground classification algorithms break all the time, because there are slopes, there are retaining walls. A sheer concrete wall would not be considered ground unless it was a retaining wall and the ground is there. So that means the ground goes over and then drops 90 degrees for however many feet the retaining wall is, and then becomes ground again. That breaks nearly every ground classification tool, and requires a lot of manual fiddling to be able to deal with that sort of stuff. So automatic ground classification tools are one of the many, many tools that pretty much all point cloud processing softwares will have some variant of automatic ground classification. And they're good, but they all right now require additional manual work to get it to be actually reliable, to get it to work on slopes and retaining walls and things like that. I will take this moment to acknowledge the incredible advancement of AI tools and machine learning tools. And as much insanely cool stuff as there is going on in AI, that's mostly in the language space. The actual real world 3D data analysis space, from a technological standpoint, has been lagging behind. There is a lot of really impressive AI tools and automatic classification tools out there that are using new machine learning algorithms, and they still have enormous amounts of false positives and false negatives and require a lot of human cleanup right now. That's just the way of the world. That said, you should be using automatic ground classification tools, and you also should be manually reviewing them and cleaning them if you want survey-grade accuracy. And the hardest part when you are actually classifying ground data is actually going to be low-lying shrubs, low-lying grass, low vegetation. This is a question that we get all the time. How do you deal with grass? And we get this with both photogrammetry and LiDAR. And the answer is, this is the hardest part for any aerial surveying, is low-lying grasses. There are a number of different methodologies that you can use to analyze these, and none of them are perfect. For example, some people like to assume that a low grass field is of uniform height and then do an offset, right? Maybe you measure it somewhere, it's 18 inches worth of grass, and you just drop the whole surface by 18 inches. That is typically a pretty bad methodology to do it, because the surface, the actual grass and vegetation itself, is pretty much never uniform. It has ups and downs as well. This is where, again, a really good LiDAR sensor and a good data analyst is worth their weight in gold, because being able to look at a site, calculate the spread, see how much LiDAR penetration there is, and tweak the actual ground classification algorithms within a certain area is going to be your best bet to do it. But this is still an imperfect science. Low grass is the hardest thing. The most important part for us is when you are creating your final map is to label vegetation as a lower accuracy sort of topo point. You can put in your topo points, you can do your offsets, you can run low pass filters, you can do all sorts of cool stuff, but it's a really important part to just communicate with the end client. This is grassy, like, double check this data. There is do not expect in any low grass, doesn't matter what LiDAR sensor you use. Even if you have $1 million LiDAR sensor, it is not going to be 1/10 of a foot accurate to true ground in low grass. It is just the most challenging part for any LiDAR sensor. So that's kind of the process, the basic process from a high level of ground classification, which is the first step that we do, is classifying ground. Step 2, once you actually have successfully classified your ground, is what we call surface rasterization. This is not a necessary step, I should point out. We think it's necessary. We do it on every single project, but we think rasterizing your ground data into a digital terrain model, a raster surface, is really, really important for a number of reasons. Very, very briefly, primer, what is raster data? Raster means you go from vector data, which is 3D points and polylines, and actually turn it into pixels, into cells. There are different ways to use it. For example, orthophotos, an image, a picture is actually raster data because it has horizontal and vertical rows of pictures, and that's of pixels. This is another way to look at it from a very rough standpoint. Vector data is going to be your actual, exact lines. Raster data is going to be pixels. This is deliberately low resolution. Your eyes, typically with a high enough resolution, can't really tell the difference. But the idea is that what you actually do, you are combining a number of LiDAR points in a given area into a single value. And the reason why this is so important to rasterize it is because point clouds, as part of the name, they are a cloud of points. They are not perfect. They have noise in them. The L1 had more noise than most sensors even. The L2 has gotten a lot better. But again, every sensor still has noise from numerous sources. All of the error that we talked about before it causes different sources of error and noise, and it creates this cloud. And what is really, really interesting, a really kind of, if you're a stats geek like me, any one of those individual points may have half a foot worth of noise. So you might say, oh, well, if the LiDAR sensor is half a foot worth of noise, it's only half a foot accurate. But that's not true. Because of something called the central limit theorem, this is normally distributed error. So what you can actually do, you can average it out. And the average of these points, the average of the noise in a point cloud, is actually more statistically accurate than any one point itself. So here's what a path profile view actually looks like on this. So this is, again, we have some ground with some, it is a profile view of ground points in brown and vegetation in green. And we've rasterized it in a couple of different ways. So the top of those three pictures has no rasterization at all. It's just the point cloud. You see there's an awful lot of noise. The middle one has some smoothing. You can actually see there are some spikes. There's a good amount of noise. And the bottom one, the analyst will have changed the actual smoothing level to and the bin size to a different level to smooth it out. And the data says that that surface at the bottom is the most accurate one. But it is one of those things that, again, it takes a skilled analyst to be able to work it out. So what you do, you classify your ground points into non-ground points, and then you rasterize the noisy ground and imperfect ground points to create your final DEM raster. And this is a photo that I really love because this is a real project. This was flown a while ago, though. So this is what the actual photogrammetry looks like. Tons and tons of trees, tons of vegetation. You can kind of see, if you watch a lot of satellite data, that there is a stream in there. And then here's what the actual raster data looks like. So again, this is raster. This isn't vector data. It's rasterized to a bin size of probably about 1/4 foot. So each pixel is about 1/4 of a foot. And it has so much detail in it that I really love. If you look very, very closely in here, let's see if I can highlight some of this. If you look very closely, you can even see fallen logs. And that just goes to show the level of resolution that there is on this, that when a log falls in the forest, do you consider it ground? And in this case, we did consider it ground, and it's just a slight little bump for that little spot. But this is what a DEM raster file might look like. Now, there's a lot more processing you can do because obviously this is still noisy. There's still bumps for every single tree. There is that stream there, but there might be more information that we need. So we'll get to that, the next steps on that, once we get into the actual line work drafting. But while we're still in the point cloud, the next step in point cloud processing is feature classification. This is going to be things like buildings, power lines, objects, vegetation, fences, walls, dirt roads, cars, noise, power substations. There are so many different things that you can classify. And you should always start by asking yourself, is this worth the time? Point cloud classification, particularly classification beyond just ground classification, is one of the most time-consuming things you can possibly do when you are working with LiDAR data. So always ask yourself, do you actually want it? Because, I mean, heck, you can create all of these different classes. This is what counts as low vegetation. This is what counts as medium vegetation. This is high vegetation. Do you mark power transmission poles different from power distribution poles, different from telecom poles, different from lighting poles? Or do you just care about it's a pole or it's a ground or something like that? There are different circumstances for all of these things. We do a lot of work with power line companies as well, where you can't just mark the wires. Each wire needs to be marked in its own separate code, depending on which phase it's on, so that it can actually be traced as part of a broader power line project. That's enormously time consuming, but really important for when you are doing power line surveys with LiDAR data. Also, while you're working this, it's another one of those things like with ground classification. Automated classification tools are improving rapidly, but they still create a lot of error. Manual cleaning is virtually always required, even with the most advanced automated tools here. There are branches that might look suspiciously like a power line, or vegetation that might look suspiciously like a car or like a building, and it just picks stuff out wrong. So I would say before you actually really get into it, you should ask yourself, what classes do you really need? This is another interesting one that we've had to have a number of back and forths with some of our clients, where a client says, hey, we flew a site with LiDAR, we need it drafted into this, and they'll send us a PD, like an Excel file saying, and here are the codes that we need marked. Here are the different classes. And we have to look back at them and say, look, we can mark every single class that you sent us here, and it'll have 100 different classes, but it's going to cost a fortune because there are 100 different classes, and we don't want to model every single darn one of those things. Let us know, what do you actually need? We'll do it. It's just going to be really expensive, but you usually don't need all of these different classes. You don't need 15 different types of water. You don't need a dozen different types of buildings. Again, some people do. Industrial buildings, low-rise residential, high-rise residential, those different building types matter, but you don't always need it. And in fact, you usually don't. So be judicious when figuring out what classes of point cloud classification do you actually need. And then power line modeling, this is another one of those examples. This is a huge and growing use case for actual LiDAR mapping. It is also very time consuming, designed for really specialized software typically that utilities need. But as the grid continues to grow, there is a lot of work to be done in power line mapping. So that's one of the services that we certainly offer. But it also requires a unique set of skills. For example, interpolating gaps where power lines weren't detected. Big, thick, high voltage power lines are typically pretty easy. The thinner the wire, the further away from the sensor, the worse the lighting conditions. Sometimes there might be gaps where it was just invisible for whatever, or the LiDAR sensor didn't pick it up, so that you actually have to interpolate across it. So all of that can be done. So the question is, what software do you use to do it? If this is all time consuming and all of it works, what are some of the leading softwares? Well, once again, there's no possible way I could cover all of these in an hour or even in a full day. I am certainly not an expert in every one of them, but these are some of the leading softwares that are out there. I will say that, again, it really depends on the industry that you work in. People work in different ones and they actually like them. ArcGIS people love ArcGIS LiDAR. It's not my favorite. I am most familiar with Global Mapper. That's, again, purely on personal preference. It's a Swiss Army knife, even if it is not the most efficient tool in the world. Some of our analysts really like TerraSolid. A lot of other people like LP360 if you're in the GeoQ system, Leica if you're in the Leica system. Carlson is actually completely capable as well. None of them is magic. There is no magic bullet to actually getting all of this stuff done. It's just about what system you're in, long learning curves, expenses, licenses. The other thing that I'll admit, most of these softwares are actually pretty darn old. They are not modern, advanced software that is on par with some of like the latest and greatest softwares that we're used to. These were designed 15, 20 years ago. And yeah, they've gotten a lot of updates, but whether it's PLS-CAD or TopoDot or even Global Mapper, you just kind of can feel that they're a little bit older. They're a little bit less optimized. And so maybe a new one will come along soon, but right now, these are some of the softwares that are out there. Again, no magic bullets. While we're on the technology side of things, though, I want to talk a little bit more about more than just software, because another challenge with every one of these softwares is once you start collecting drone LiDAR data, it's really dense LiDAR. There's so much data, it makes your computer run slow. So how do you deal with it? And one question is whether or not you should thin your point clouds. And this is a really, really interesting one and something to be careful with, because thinning point clouds can make less data and it's easier for your computer to work with, easier for humans to work with. It's faster. It doesn't clog up your systems, but it also can lose a lot of the data that we worked so hard to make at the earlier stages of everything. So be very careful when thinning point clouds. It can introduce additional accuracy. So I would say just be careful with point cloud thinning wherever you use it, because it can definitely reduce accuracy. Another way to actually make your workflow better if it's not thinned, and if you're dealing with too many points, is actually to tile out your point clouds. Most of the LiDAR systems will let you save it into 5 or 10 or 20 or more individual chunks, whereas each chunk is actually going to be much more manageable to the system, right? Dealing with a 50 million point cloud is way more manageable from a compute perspective than dealing with a 2 billion or 5 billion point cloud. So thinning and tiling, use carefully, but they can be really beneficial. Again, and also I should say, this goes back to the thing that I talked about a lot, which is balance. If what you really care about is speed, then you should thin your point clouds and acknowledge that there will likely be some inaccuracies in there. And the other thing that people talk about is computer hardware. I always like to point out, I'm a tech geek. I like computers more than most people, but in pretty much every circumstance, more expensive computers will not solve the challenges you're facing. If your computer is running slow, you double your computer, that sort of thing, it won't fix it. A lot of it is because of unoptimized software and unoptimized workflows. An efficient workflow is way more valuable than new hardware. That said, having plenty of RAM is really important for some softwares, but a lot of times you're bottlenecked by single core processing speed, by older non-multi-threaded processing things. This is not like an AI machine learning. You need the latest and greatest GPU. That is rarely the processing bottleneck for LiDAR processing. And I always like to point out, a good workflow can run on nearly any computer. Most of our team uses gaming laptops with a number of different things, but in general, a good workflow really matters. All right. And now I'll keep moving quickly because we don't have that much time left. I told you there was a lot of content in this. I know I'm always content dense, and this might be a new record for me too. So let's just keep blasting through this last step, which is going to be step 3, actually making a map, starting with drafting and feature extraction. Like I've mentioned before, that's an unfair characterization. A lot of drone people in particular, drone service providers or people that really care about just the drone and LiDAR side, stop at a classified point cloud. They don't actually make a map. We make maps. That's the most important part. And if we're being honest, this is one of the most tedious, time-consuming, and challenging parts. It starts with line work drafting, where you take that rasterized surface, which is still typically a pretty large, pretty cumbersome file, doesn't open well into maps, has noisy, jagged contours, and you actually need to draft it into a lightweight vectorized tin surface where you have things like road center lines, curb and gutter and flow lines, brake lines. You draft your actual retaining walls, things like that, to create a vectorized tin surface that is more lightweight and easier to use and easier to manipulate. There are a number of other reasons with tin surfaces that I'll cover in a second, but drafting is really important to create a tin surface, as well as identifying and marking all of the other features that are in there. This makes smaller files easier to transfer and use than a point cloud, necessary format for many maps and deliverables. Most surveyors, I really personally, this might sound weird, I actually hate point clouds. I view them purely as an intermediate step. They are an intermediate step to getting to a map. An actual good, well-made map is so much more useful than a point cloud. It is smaller. It is easier to read. You can turn the right layers on and off. You can send it in an email. You don't need a specialized computer or specialized software to view a good map. So that's why that's one of the many reasons why line work drafting is required. And again, it's tedious. This is a very manual process. While you are drafting, though, be aware, and I say this before, I've said this in the other presentations as well, photogrammetry is simply better with 2D features. When you are looking with imagery, you can mark curb lines, paint striping, building footprints, concrete, edge of pavement, edge of road, manhole covers, railroad tracks, the whole 9 yards. It is so much easier to draft 2D features. And by the way, you can draft 2D features and then either drape them on top of a LiDAR-derived surface or use photogrammetry derived for the elevation data. But this is part of why a blended workflow is so critical. Drafting 2D features with LiDAR is awful. It is very time-consuming, and it is not particularly accurate. You want to extract your 3D features from a point cloud. We actually try, other than ground surface, we typically want to avoid drafting 3D features in a point cloud as much as possible because it is very time consuming. Extracting the tops of power poles, for example, yep, you pretty much have to do that from the point cloud. You can't do that from photogrammetry, but you need to do it in profile views. You need to find the right center point. You need to adjust for the noise. Typically, this is what it looks like, what parts of it might look like in a software like Global Mapper, or from a top-down view, you create a profile that's right through the dead center of a power line, and then you mark your points from there. Another part of drafting is what we call making a final surface is the next step. This is where you actually create that final tin surface that I was referencing before. When you are doing this, you need to decide when you're making the surface, do you use LiDAR or photogrammetry data? Because most drone flights are going to have a blend of them. And as I've mentioned before, photogrammetry is generally better on hard surfaces, whereas LiDAR is far and away better in vegetated areas, especially with trees, brush, anything like that. Once you actually create that raster surface, you can extract LiDAR-derived topo points to create a tin surface that you then blend with your photogrammetry data. And so this is one of those battles between raster and tin. A lot of LiDAR analysts will just say, I'm going to create a LiDAR surface. I'm going to extract 1 point, 1 topo point every 1 foot and dump it into this huge tin surface. But it can be done way more elegantly than that. By creating a proper tin surface with everything that's actually managed differently, then you can blend your tin surface with photogrammetry data and LiDAR data and even ground data to create a surface that is smoother, it is prettier, it actually looks nicer. People like maps that actually look nice. It is more lightweight, easier to put into CAD and that sort of thing. We got a couple of questions here that I want to address. First off, we're in the Trimble Business Center ecosystem for all of this stuff and occasionally use Metashape. Any advice? Ooh, boy. I don't like Trimble Business Center. This is a totally personal preference. I hope I'm not making any enemies by saying that. I've used Trimble Business Center as well. I find it to be particularly clunky. That's part of why I use for, so I can tell you my personal view that of the softwares that I use RTK Library for a lot of open source GNSS processing. I use Global Mapper for most of my GIS and 2D features. I'll use Virtual Surveyor for really efficient extraction of data. Civil 3D is our CAD engine, and Pix4D is going to be our photogrammetry engine. That's actually one of the challenges with that. That's a ridiculously expensive suite of software right there. Each one of those softwares is, well, aside from the open source one, each one of those software is typically going to be at least $1,000 a year. You can run up a software bill like crazy. And I say that those are my personal preferences. Like I said, Pix4D is my favorite of the photogrammetry engines. Metashape is, it's viable. There are definitely some geopolitical challenges with it because Agisoft is a Russian company. And so there's obviously just a lot of complexity there that I'm not going to get into right now. Pix4D is Swiss for what it's working. That's our favorite photogrammetry engine. And then we got just another question we'll get through right now. When looking at the computer being slow, would you recommend building a decent computer to be able to process things faster? Nope. Regular computer, when I say regular computer, if it's actually reasonably powerful and has been made in the last 3 years, then you are fine. And even when it comes to building a custom computer, you can go over the top. We've seen people that have built $20,000 single computer rigs for LiDAR processing, and they are the teeniest little bit better than anything than a normal gaming computer. Right? Quite frankly, a good budget to think if you're buying a powerful computer for photogrammetry and LiDAR processing, have a budget of about $4,000, and that'll put you your 95% of the way there, and squeezing that last 5% of performance out will cost so much more money. So about $4,000, and built in the last couple of years, is about the range to go for if you want a good, powerful enough computer. All right, moving forward, as we only got a couple minutes left. I want to touch real quick on accuracy and point density. I'll skip over this slide. You can read it later if you want when we got the deck, because the visual just shows it so much more cleanly. Accuracy and point density. This is a very exaggerated version of what the difference is between accuracy and point density. On the top, if you have all of those individual points to define the surface, each one of those individual points might be accurate to, call it 1/100th of a foot, but it's going to be a less accurate surface. It's going to less faithfully describe the real terrain as a more dense surface. Or a really good drafter will have break lines in the right point and the right point density to go with it. The reason I bring all of this up is that point density matters, but more points are not universally better, because more points add noise, add file size, make things harder to use. There is a balance. Point density should be tailored to match the map that you are creating. If you have a 200-acre site that is virtually entirely flat, you do not need 1 point every 0.2 feet or something like that, or every 1/4 foot or anything like that. The file size would be huge. It would make Civil 3D slow down like crazy, and it's miserable. 1 point every 10 feet or every 20 feet is probably enough. If you have a lot more undulating terrain, if you have rivers, if you have curb lines, you need a higher density of points. Make sure that the point density is tailored to it. The better, and once you do that, you can actually get better overall project accuracy even without better individual point accuracy. And then one of the final steps to making a map is actually blended orthophoto creation. We've thought about making an entire webinar just on this, because blended orthophotos are such a cool thing that you can do. You have raster image from so many different sources. Photogrammetry, you can actually create an orthophoto from LiDAR data, which I don't know how many people are doing this or how well known it is, but you can create ortho imagery purely from LiDAR data, which is really cool. Same thing with, you can make a LiDAR intensity raster ortho image, which you can do, and blend in satellite data. And the best thing to do is blend in the best of both worlds. So this is an example of a project site where this is the photogrammetry orthophoto, and you can see it looks pretty good for most of this, but it has a whole bunch of black patches because photogrammetry does really poorly with vegetation. And so what we do is, underneath the photogrammetry one, because photogrammetry, when it's there, is going to be the highest quality orthophoto, underneath it, we put in our LiDAR-derived orthophoto. If you look really closely, it's a little bit grainier. It's still incomplete, not as high resolution with 2D features, but it fills in those gaps really well. And then if there are more gaps, you can even underlie all of that with satellite data to create a final blended orthophoto that is going to be the highest quality data that you can. That's the basic process. And like so many of these things, the actual technology for it is all over the place. So many different softwares. People have all kinds of different preferences. I have mine. Other people have theirs. There is no magic bullet with this. Except for one, I should say. There is one thing that is a magic bullet, and that is working with Aerotas. This is what we do. We've been doing it for 10 years. You fly drones, send us the data, we process it, LiDAR, photogrammetry, everything I just showed you, that is what we do. We help you create these deliverables so that you can save time and get money, improve your deliverables. So with that, if you are interested in learning more, you can reach out. We are going to be, please do reach out, because we have a bunch of resources. I referenced other webinars, other documentation, both by Aerotas and everyone else. We'll send it out. And like I said in the past projects, if you want to process your data with Aerotas, if you're a new customer, we would love to offer you your first project up to $500 free or $500 off. If it's a bigger project, scan the QR code. We've opened that link up right now for them. Or you can always email me. My personal email is logan@aerotas.com. If you've sat through this entire thing, you definitely have earned the right to send me an email. But we would love to work with you. That's what we do. We've got so many announcements coming up. And boy, I see there are a bunch of questions too. And I'm sorry I couldn't get to hardly any of them because there was so much content. And we are now, I want to be respectful of your time because you've been so nice to give it to us for the last hour. So I'll wrap things up. If you got questions we didn't answer, scan the QR code, send us a note, send us an email. We would be happy to answer it offline. So with that, thank you so much for your time and attention. I appreciate it. I wish you all the best in your LiDAR programs going forward, and have a great day.